An atom is about 1,000,000 times beyond the limit of what can be seen by a human eye. If you were to stack 6 magnifying glasses back to back, each with a magnification factor of 10, would you then be able to see the atom? The answer, frustratingly, is no. Even if you had perfectly manufactured lenses and stacked them in the perfect position, you'll eventually hit an impassable limit. So, what's the holdup? Well, visible light has a wavelength between 400 and 700 nanometers. If you try to magnify things below roughly the wavelength of the light you are using, the individual waves start interfering, and all you see is a blur. This is known as the diffraction limit, and is a firm roadblock prohibiting the imaging of anything smaller than about 200 nanometers with visible light. But you might have seen pictures of tiny cell parts, or even of atoms, which are on the scale of nanometers, far below the diffraction limit. This is possible by the use of electron microscopes, which leverage the fact that electrons have an effective wavelength 250,000 times smaller than visible light. So, we don't beat the diffraction limit, we just get a different threshold. In 2015, a group of researchers found a novel solution to this imaging problem. Instead of making better microscopes to lower the diffraction limit, just physically enlarge the details themselves to be above the diffraction limit. This is the foundational idea behind expansion microscopy, a technique where a polymer gel is introduced into cells, which then absorbs water and swells up greatly, increasing the size of all features of the cell. Then, a traditional microscope can be used for imaging, greatly reducing cost, increasing throughput, and allowing for a traditional contrast usage. One of the inventors of this technique, Fei Chen, was a graduate student at the time, and now runs his own lab at the Broad Institute, researching spatial and temporal genomics.